Hey guys, how's it going? Welcome to another episode of Ferris Makes Emulators. It's episode 59. We're almost at 60 of these things. That still just blows my mind every time. Today is going to be kind of a different stream. Maybe not so different. But, so we've been working on libretro front end for Rust Boy. I'm actually going to pull that up. Excuse me, I'm actually going to pull that up here. Move around some USB things. But I want to pull that up so I can show you guys some of the progress that I made last weekend. Had a pretty busy weekend working on that a bit. And that's going pretty well. I also made a big ticket about what's kind of left on that. And there's a lot of stuff. But let's see here. Russia Boy, libretro now, and we want to do something like, I think it's in here. Downloads libretro. Oh no, it's RetroArch is the front end that I'm testing with, and that should be RetroArch, and I'll do -- verbose capital L, and then the target. This will be target /release / Rustoboy libretro.dll, and then add my argument. Almost there. Lots to type currently, but it's not too bad. And that almost worked, except I think it didn't like that I did dashes here. I know you guys can't see what I'm doing here, but it will all become clear in a moment. And there's actually a bug in RetroArch that I need to look into that I'm hitting right now. But when I stop hitting it, then we'll see. All right. So this is a RetroArch, which is just general kind of emulator front end. For libretro cores, made by the libretro team, and it generally works pretty well. We have stuff like some options. You can have some like states and stuff, pictures, all that stuff. Don't actually support all of that yet in Russia Boy, but we have a couple nice things like full screen, which I can't really show at the moment. Also controller support. Normally works. Maybe it's my N64 controller that's hooked up now. Or maybe I just don't have it hooked up right. Anyway. All that stuff more or less for free, at least comparatively. Lots of stuff like pausing, unpausing. Just things that you would expect from a front end. Toggle full screen, different window scale modes. Make this real big. Reset, even. So all kinds of stuff. So this is going generally pretty well. Yeah, I will put an alias on that at some point. Usually I just do up enter, so it doesn't really matter when I'm working on it. That's why I haven't felt the pain enough yet. Anyway. It should have fancy shader support. I haven't explored that much. But anyway, just wanted to show that that is actually going pretty well. I also made a big ticket about it this weekend, just like brain dumping all the things I know that I want to do for this. Also had some chats with libretro guys behind that stuff. And they're more interested than I thought they would be about having a Rust course. I'm pretty excited about that. But there's a lot to do before this is really mature, so I got to work through a lot of that first. Anyway, while working on a lot of this, things are going pretty well. But I had to revisit a lot of the bootstrapping stuff, which luckily, because we did the architecture in a way that makes a lot of sense, that was actually really, really easy. And it just so happened that 8littlebits, who's in the chat, hi 8littlebits, he had asked, or was it, I don't remember exactly how it came up, but it came up that audio and emulators is kind of a black art kind of, or like a dark art black box kind of thing. And I thought about it for a minute. I thought, it kind of is, isn't it? Like it's pretty obvious how some bytes in memory can correspond to pixel colors. It may be less obvious how the same kind of thing works for audio. So I would really like to talk about a lot of that. I want to talk about a couple things. I want to talk about how audio generally works for a lot of systems, especially these retro systems. I want to talk about the architecture we use in Rustro Boy to model a lot of this, and then I want to talk about timing behind a lot of this stuff, as it's actually surprisingly simple when you have the right mental models, but you may not have thought about it much before, so it's good to have it explained. And I also want to talk about a little bit about how modern audio APIs look on host machines. They generally follow some of the same patterns, not always, but enough that we can talk about them in a pretty general enough way, I think. So I think this would be fun to talk about because it also again touches on that architecture and why this was actually pretty easy to hook up in libretro. So I want to talk about that also to kind of show it off because I'm actually pretty happy with the solution I've kind of arrived at for doing this kind of stuff. I'm not that prepared, and I did that on purpose because I thought there might be a lot of questions during the stream. So just shout out if you want. By the way, speaking of shout outs, hi to guys in the chat. 8littlebits, like I mentioned earlier. Try later. SK Test, SU's, Cluewash, Zokwar, Mojo Bojo. That's a fun one to say. Hope your migraine's a little better, dude. Dark Second, Wister Tobe, Mad Moose, Skeleton, G Superland, Local Hoster, gang's all here. Cool. All right, so I think I'm going to start with like super basic stuff, right? I may jump around a bit here just due to how things work nowadays and how they kind of used to work for audio. But I want to start super general, just kind of describing what audio is even, right? So audio is basically movement of waves in air, typically. So you have, for example, a speaker. It's got this cone thing, and this cone actually has a membrane here. So this is kind of a side view, but if we look at it from the front, it's just this big old circle with this cone here. And what happens is there's usually a big old magnet right here, and then we have an electromagnet here on sort of the back of the cone, or usually it's in the middle, I guess, because that's the part you're going to move. And what happens is that you send a signal with varying amplitudes to this electromagnet. And what happens is this will either repel this magnet here or attract the magnet there. And if you do this in sort of a up and down motion for this amplitude here, this will move back and forth, and it'll move the sound back and forth. And that travels through the air, and it hits your ears. The ears kind of look weird. Hits your ears, and then your brain does some stuff. There's some sensors in there that send signals to your brain, and then this is a brain. And then you perceive that as sound. Yeah, paint drawing style is very important for describing things accurately and precisely. It's just the best tool for the job. Dark Second says it's like video in one dimension. It kind of is. I would argue that it's the way we're going to be looking at it. It's kind of like video is almost three-dimensional in that case, and audio is going to be two-dimensional. Because I want to include the time domain. But you can draw a parallel here where if you think of sort of a video signal as a 2D grid of brightnesses, so you can kind of think of it as a little height map. But of course, this would actually be like four-dimensional, I think, because you have a height map in 3 dimensions. I don't know. I'm bad at math. But if you imagine it like that, then this is kind of the same thing where you're basically just graphing the speaker position in the same way you would graph height in terms of brightness for the different components of a pixel in video. Anyway, there's a lot more to it than this, but this is kind of generally how sound works, and it's very important in terms of like even just to know this at this basic of a level. Let me do a new one. So here's, I think what we get to next is how do we generate such a signal? So if we think about this, this signal is continuous. So at any point, this is just what this is. And you can generate this with some basic analog circuitry, basically oscillators that will do this. I'm really bad at basic electronics, so I'm not even going to try to explain how that works because, frankly, I have no idea. So we're not going to do that. We're going to talk about digital audio because also when we're talking about retro systems, it very quickly becomes digital. To my knowledge, there's actually very few, especially video game consoles, but also just retro computers in general, that produce analog sounds. One that may come to mind is the C64 because the SID has analog mixing and an analog filter, but the initial output from all of the oscillators is digital. Nice, man moves. Hey, Middle Voids. Hey, Michael C. So instead of thinking of this as a continuous signal, we're going to think of this as what we call a discrete signal. So we're going to break this up. And again, this is where the video analogy really comes in. If we break this up into a bunch of little slots, and we just sample the wave position in each slot, it's kind of hard to draw here, but you can imagine these little bins being sort of filled up with data and representing a wave. Now, by the way, this wave is way too high frequency for this low bins. This is what we call aliasing, but I will not try to explain that here. But that's totally what's happening to this wave, so it doesn't really look so much like a sine wave in some places. But anyway, the point is that instead of having a continuous signal, we basically have discrete steps over time. So this is still our time domain. And then this here is still our amplitude. But what this allows us to do is we can start not necessarily thinking of this as an analog signal, but as a digital one. I'll tell you what I mean by that, because it's going to be kind of important here. Yeah, I'm going to try to not mention Nyquist. Definitely not going to mention Shannon here. Unless we start compressing this. But my point is, like, if you wanted to record this, for example, you could record this as the continuous signal on, magnetic tape or something. Or you could record this digitally if you are, recording something. But you can also produce it the same way digitally. So if we have each of these as sort of a cell in an array, and each one contains, say, an 8-bit value, 0 could represent the lowest, peak that we could have, and 255 could represent the highest peak that we have, and then 128 would represent the middle. Not exactly the middle, because 0 to 255, not 256, but that would be what we would use. But if you have that, then you can actually represent a wave just by, having an array of these samples over time. Now, when we're talking about actually generating a signal like this, we wouldn't have it in an array. We would in a modern machine, but I'll get to that. But in a retro system, we wouldn't actually have that in an array, typically. What we have is a couple things. For those of you guys that are familiar with microcontrollers, this is going to be pretty familiar to you. So let's say there's our sound chip, or some kind of chip. We'll call it C. And C has a few pins. This will be an IC. Doesn't have to be, but it will be in this case. So you have, reset, VCC, ground, your typical things that you would have on a micro like this. And some of these pins are going to be some kind of data bus. So I'm just going to condense this into a thick line. Say D7 through D0. Please excuse my horrid handwriting. But this would just be like an 8-bit data bus. And the point is, what we can do is if we have this 8-bit data bus, then we can put a digital value on this port, and it will be represented, the different bits are going to be represented on these different 8 lines. If we then take those 8 lines and put them into what we call a DAC, which is a digital to analog converter, then we can actually send this out to our little speaker. So then what we have to do is we have to put all those little audio samples on this bus really fast, right? See kind of where I'm going with this? When we have the different steps of the signal over time, we're just going to, as time progresses, put different values, from 0 to 255 onto this bus. So this is kind of, the reason I'm describing it this way is because in most retro systems, when we talk about it, especially from an emulation perspective, this part here is kind of all implied, that this part all exists, and that this is kind of going to be the output of our sound chip, is this over time, whatever's on this bus. And there are different details with what we have to do with those values. For example, in hardware, you would just put them on this bus and you would hold it there for as long as the sample lasts. So if we have, all these samples here, this right here is not, this right here is, time t, like sample time t. So you'll set the value of this port to like this value and you'll hold it there for time t. And then after that, you'll set it to a different value and hold it there, a different value, hold it there, different value, hold it there. So that's all that's happening in hardware. In software, what we do is we actually generate all of the values and we do actually stick those in an array. And we give that to some API or part of the OS that will then, route that where it needs to go and send it to your speakers. But don't think about that yet. Just think about the fact that we're going to be having some digital output that's going to change over time. So that leads us to a couple things. First of all, I do actually want to talk about this t value because I want to talk about how long or short this is. So the human ear can hear frequency. So frequency is, we have a wave here. Frequency is if you go like peak to peak. Your frequency is how often these peaks happen, basically. So you have this peak to peak thing here is called a period. And if we take is it period over time, we get a frequency. Think that makes sense? Time, by the way, is usually measured in seconds. So then frequency is in hertz. Hertz is just repetitions per second. So not too fancy. So the human ear can hear signals from about 20 hertz up until about very high frequency, 20 kilohertz. And this isn't kilohertz, this is kilohertz. So actual 1,000, not 1024. This is about the range of human hearing. So this is it. I've been using left to right as the time domain, but this is the frequency domain. We have 0 is out down here, and we could technically represent like anything, but we have about 20 here. Now, I said I wasn't going to mention Nyquist, but I'm going to have to. And I'm going to hand wave a lot of this because you don't have to understand it. You just have to kind of know it. That to represent a signal when you discretize a signal like this, in order to accurately represent it, like if you wanted to represent a sine wave, you need your sample rate, which is how many of these samples happen per second, again, measured in hertz. You need your sample rate to be at least 2 times the max frequency that you want to represent. Again, terrible handwriting. But this allows you to accurately represent a signal. A really, really quick demonstration that I can do with that, let's see if I can just kind of draw this. If you take each sample and you did low, high, low, high, what you would get is this roughly approximates a sine wave that is the highest, that is literally half your sample rate in its frequency. So that basically tells you that's the highest frequency you can accurately represent. If you try to represent higher frequencies, this weird thing happens called aliasing, where you actually, like, you try to represent a higher frequency one, but then if you sample it at the right places, you actually get a lower frequency sine wave. It's just kind of weird when you try to recreate it. But we don't need to worry about that. We just need to know that we need at least 2 times the max sample rate, or we need 2 times the max frequency that we could represent as our sample rate. So for human ears, the maximum frequency you can hear is about 20 kilohertz. And I mean, this is high. Like, if I sat here and played a 20 kilohertz sine wave, a lot of you probably wouldn't hear it, to be honest. I don't think I can hear that high anymore. I think the highest I can hear is around 18. But, so this leads us to a couple common sample rates that are used in computers. For example, one of them is 44.1 kilohertz. And yes, I'm using lowercase h, just deal with it. Hand wave. So this is a CD audio sample rate. And a lot of things still use this. It's extremely common. And then half of this is, of course, around 22 kilohertz. And I did say about 20 kilohertz, right? So I think that there are some people who can hear higher than that, but you're not getting much higher than that. So this is CD sample rate. 48 kilohertz is a little more common recently. To be honest with you, I don't know why, because I don't see any advantage. I don't understand why you would want to do that. It's just more data. For what I can tell is zero benefit. So I don't know why that is, but I just have noticed that everything's 48 kilohertz. If you're working in pro audio, a lot of the times you'll use 96 kilohertz. I've also seen 120 kilohertz, especially if you're working in recording. A lot of this can make sense. Usually you don't need it, even if you're working in audio, but that's a whole other thing. You'll also see, going the other way, you'll also see some other numbers. The Virtual Boy is actually 41.6 repeating kilohertz. The documentation will tell you it's 41.7, but I've done the math and I've done some really educated guesses about some of this. And it's definitely 41.6 because it turns out that this leads to a period that's exactly 480 system clocks. So this is definitely what it is. And then all the other counters for all the other timings that it mentions in the docs are like super even numbers of that period, like 160 times that period, 320 times that period, 40 times that period. So it's definitely this, even though the docs will round this up. Super Nintendo is 32 kilohertz. And if you've ever listened to a Super Nintendo and thought that it sounds kind of soft, that's actually because it literally is. The highest frequency it can represent is 16 kilohertz, which is lower than like CD audio. So it will actually have a warmer sound because a lot of those high frequencies will be cut off. You'll see with lower quality samples or older samples where the hardware, computer hardware couldn't necessarily store that much data or play that much data back. You often had, 20 kilohertz, or 22 is another really common one, 11 kilohertz, and I think oftentimes we get like 11.5, 11.25. These are just sample rates you'll see in the wild. And what this actually means, again, is they're representing a wave in discrete pieces. And it's how many pieces are there per second. That's all it means. Oh, that's interesting, SKTS. I actually didn't know that. But then that would make sense to me if 48 kilohertz were related to timing and TV signals. I don't know how it would be, but if it were, that would make sense that would be a reason to use a sample rate like that, because you really, like, this is basically your lower bound for things that can represent basically anything that you'll actually hear in the real world. And this is not too much higher than that. So that's, if it's more convenient mathematically, it makes sense. Because you could go the other way where you go a little bit lower than that. And then suddenly you're actually missing part of the sound picture. Okay, so back to our retro systems. So you have that bus, D7 through D0. And something is just putting digital values on that, at that rate. So let's say this were doing it. I mean, we can make this really easy by just saying let's say it were 32 kilohertz. Ah, of course, 24 FPS. Yeah, then it makes perfect sense. So let's say you were doing this. Let's say you were doing this, and let's say this was your CPU. It wouldn't be, by the way. But let's say it were. So your CPU had some kind of port on it. We can actually call this a microcontroller. Your microcontroller has some kind of port, and you're using the CPU to just sit there and shoot out waveforms. This would actually take a lot of CPU power, especially for retro systems. If we do the math, 32 kilohertz. So we can just take 1 divided by 32,000, 32 kilohertz. And we get 1.00003125. This is the portion of a second that every time one of these time units passes, we need to put a new value on this bus to match the sample rate. Just to match that to something, the C64 CPU runs at 1 megahertz. So if we take 1 divided by 1,000,000, right? That's this unit here. And you can see that that's already actually kind of close to this. We're only about an order of magnitude smaller than this. And remember also that for example, the C64, the fastest instruction you had was actually 2 cycles, right? So we have to, we can't actually get this resolution. So it's actually more like 1 divided by 500,000. And this is the max rate that we can do anything at on this CPU. And again, we're still about 1/16 of the speed that we need to do. So in like 16 cycles, right? If we did 16 instructions here, then we're actually past our limit here, right? So the 16 instructions that you would have to produce the new waveform, this uses a lot of CPU compared to what you had then. Does that make sense? Nowadays, it's not that much compared to what we have in terms of computing power, so it makes sense to generate a lot of audio samples and send them to a buffer. But back then, this did not make sense to do this with a CPU. So you would often have dedicated hardware that would do this. So instead, you're inside your micro or your usually there would be custom silicon here in your system design. Let me just your 8-bit system, for example, would have an off-the-shelf CPU. You wouldn't design your own CPU. You might buy some CPU IP and put that on a chip with some other stuff, but it was more common to just use an off-the-shelf chip. That would communicate with a couple things. One of them usually being at least a video chip. And it was very common for things like video chips to either also contain audio, and the idea being that if you're already manufacturing a custom chip, you might as well put both things on that chip. But it may also be that instead of producing one chip, you may produce something more than just game consoles. You might produce arcade machines as well. So then it makes sense to actually manufacture them in separate chips. Because you could do, 3 times the run of these that you do of these. And suddenly it's cost effective to have them in 2 separate chips. So a lot of this was guided by economics, how this was designed. But the important thing here to note is that your CPU would just be kind of connected to all this through some memory mapping. And this separate hardware would spend all of its time, again, outputting on a similar bus to what we saw earlier. Yeah, now we should all use Facebook New Flicks. I actually haven't checked that out yet. I should. least see what that is. But I can tell you from a bird's eye view, when I saw that go by in my Twitter feed, I'm just like, ugh. Anyway. But what this allowed us to do is we can set up, we can tell the audio hardware. The audio hardware would usually have a couple oscillators. And those are, like I mentioned, would generate kind of a signal. A lot of the time, though, these oscillators, they're just basic counters. So we have a clock signal that is going to run our CPU, for example. Let's say this was 1 megahertz. It almost was never 1 megahertz, by the way, because a lot of this was actually driven by some multiple or divisor of the TV signal, and that was so that the entire digital part of the machine could be driven with one clock, which simplifies a lot of digital stuff. I'm not going to get into setup and hold times for registers either. But the important thing was there was like one system clock that kind of drove everything. And it was usually related to the color clock, especially of the output video signal. Anyway, this clock would run to the CPU, it would run to the audio chip, and it would run down to the video chip. And many times there was something like, the clock was actually, 12 times the speed it needed to be because the video had to produce many, many pixels very quickly, and then it would be divided for the CPU or divided again for the audio. It wouldn't really matter. But yeah, that's kind of the idea, is that this clock kind of goes everywhere. And what you do with this clock, so this clock is literally just like a pulse wave. In fact, the way that this was often generated then is you'd have a physical crystal. And again, I don't understand the lower level electronic parts of this, but if you run electricity through a crystal the right way, and with a little feedback network, it will actually oscillate at a certain frequency. And then you can filter that signal to make it a square wave. That's sort of the general idea there. And that's really all you need to know, is that something is generating this clock. But this clock will go up and down at hopefully a regular rate. And again, the frequency here might be, 1 megahertz. It wouldn't be if this were 32 kilohertz probably, but I think you get the idea. Yes, like Jeff, it was extremely common for systems to run slightly faster on NTSC than PAL because of the TV signal differences. Because PAL's at 50 hertz and NTSC is 59.97 or something. And so they would often clock the entire system a little bit differently, because it just made a lot of things easier to manufacture. Basically, digital circuits are a lot easier to build and understand if the clocks are a single rate. Do I know how modern day CPUs change their clock rates? To be honest, no. I think there's some analog components there that I don't really have a very good overview of. But that's kind of out of the scope of what I want to talk about today anyway. But where was I? Yeah, so this clock is just this thing that oscillates. And so what you can do is you can do a couple things. First of all, 1 megahertz is way too fast for us to hear, right? So like this audio chip, the simplest design it could be is it could take the clock, right, and just shift it. So if you imagine, let's imagine our simplest audio thing that we could have, and this is a stupid audio chip, but let's just think about some of the designs here. So we have a clock input, and remember that our clock is going to be doing this. And then we have our, D7 through D0. So here's totally a valid implementation of an audio chip. We'll just route the clock to data 7. And then we'll tie all these other pins. I should be drawing little dots here, but I'm trying to save time. We'll tie all those to ground. And do you see where this is going? Because what this will produce then is a square wave, which then goes straight to our speaker. Yeah, the NES, As I mentioned earlier, it was very common for a lot of these chips to be built into other chips. So like if you're rolling a piece of custom silicon anyway, it may make sense to take all of the custom logic bits that you're going to do and put them on that chip. So like the digital analog converter was also part of the audio chip. That's why you don't see it in a lot of schematics. It's usually a register ladder, but it's part of the internals of the audio chip. On the NES, it was part of that part of the CPU chip. On the Atari 2600, it's part of the video chip. It's called the television interface adapter, so it has video and audio built into that. So you'll often see those on like the, yeah, anyway. Yeah, I'm not that surprised to hear the Game Boy is as well. But I think I like to use this as kind of an example of like how simple this can be, right? Because you can, like this is kind of really close to actually how a lot of this actually works, right? Just really quick, while I have this diagram here, instead of having this, let's say we did something like this. What would happen if I did this? Instead of D7, so we're going to ground D7 and ground all the other ones, but then we route this to D6. This produces the exact same wave at the same frequency, except it's going to be half amplitude. Does that make sense? Just because it's just a lower bit. We've effectively divided it by 2 just by hooking it up to a different wire. So how big is my eraser? I need a bigger eraser. This eraser sucks. Paint is not great for doing this, you guys. But it's good enough. Okay. So that was our simplest audio. Oh, what? Now I got a fancy brush. So that was like our simplest chip. Now let's do something else that should be pretty simple. So we're gonna do our same interface here. We have a clock in, then we have some data out. And we just have to route this together somehow. So we saw how we could just route this straight there, and then we'll get something that's way too high frequency. But like let's do something here. Let's do a little experiment. If we take 1 megahertz, so 1 million samples per second. That's way too fast. We want to get in around somewhere between the 20 and 20 kilohertz range. So let's just start dividing this by 2. So 1, 2, 3, 4, 5, 6 times. We'll do 7 because this will be an easier one to hear. So if we want like a 7.8 kilohertz signal, how many times did I do this? 1, 2, 3, 4, 5, 6. Then we want to divide the clock by 6. So 4, 5, 6. So for every 6 pulses, we want a pulse that does this and then switches low for, that long again. Now, the way we do this, I'm actually not going to draw the right symbols because I don't remember what they are. But if we have a register in here, call this our reg. And let's say we're going to divide this by 2 6 times. So I said divide this by 6, but that's not true. I'm dividing it by 2 to the 6th. Then I think we need 1, 2, 3, 4, 5, 6 lines on this. So 0 to 63 is our range here. So we're going to take the clock. We're going to have a register. And this is going to be... Oops. I don't want to draw it like that. But this register is going to be 6-bit. 6-bit register. So we're going to have a 6-bit bus coming in and coming out of it. And this is also going to be clocked. And what we're going to do is we're going to have this counter here. It's going to start at 0. I'm going to not draw how that happens, but it's going to start at 0. And its output here is going to do two things. The first thing it's going to do is it's going to route back to its input. You say, how does that work? Well, what happens is that a register will only will hold whatever output value it has until the clock transitions from low to high. And then it will take its input and put it on its output. So if we have just feedback like this, not much is going to happen. It's just going to feed back into there. But we can do something interesting here. We can put in here. We're going to put in an adder. And this adder, which I'm going to draw kind of like this. Kind of like shorts. This is a 6-bit adder, and we're going to route the clock to this too. So what's going to happen is that every time the clock transitions from low to high, the value of this register is going to increase by 1, right? Now remember that this is a 6-bit signal. So if we take, I'll call this R6, which is the 6th bit of this, and we route it here, and then we take all these pins, bring them low, then we've effectively divided the clock by 64, which I think that's the number I'm after. No, we wanted one more, but that's fine. This will be 15K. But what I'm trying to impart on you guys is sort of the general structure of how this works. We can take this clock, and by using basic counters like this, we can already create something that, you know, generates pulse waves at 15 kilohertz. Right? And all we did was just do a basic binary counter. Is this making sense to you guys? Yeah, this would be very high pitched. It also wouldn't be a sine wave, it'd be a square wave. And digital square waves aren't the greatest thing to hear, but you hear them a lot in analog chips, in digital sound chips. And this is why, because they're very easy to generate pulses from your input pulse. So a clock divider can be very simply implemented as a counter. Now, you wouldn't want to drive much else with this output of this clock divider here. You wouldn't want to drive more of your digital logic on that, because you actually have some phase difference between the clock here and then what's happening here. But it's fine, because this is just going to go to a DAC and then a speaker, so we're okay there. It would sound like you're getting your head drilled in. And so if you're making a game where the point is to drill your own head in, I think this would be a decent design for the sound chip. Although you would waste a lot of lines here, because if you knew you were only going to generate pulses, then you could just do send this to the speaker in a way that's simpler than a DAC. But totally try later. R-2R ladder, I think is how you write that, which is a register ladder, is a simple DAC. And you'll often see that in chips. I'm not going to explain how that works, because I don't think it's very important. That's just how you might implement the DAC part. Hey, Drew, too. But yeah, again, the whole point of this demonstration is just to show you kind of how simple this is. And in pseudocode, it might look something like this. In fact, I can actually show you some Rust Boy code where this is super obvious. In fact, I'll show you a little bit of the VSU code here. I won't go too far into detail here, but so this is our sample rate, and our sample clock period is 480 CPU clocks. And the way I do this sample clock period here, if you just search where that is, this is actually how that exact thing is implemented in the Rust Boy code. So this is our sample clock counter, which isn't tied directly to the output, but it's just something where we just count up by 1, and then when it gets greater than or equal to this period, we set it to 0, and then we do something. Now, a little thing with a comparator like this, you kind of have to imagine how that hardware might look, but it's not far off from here. You have +1, and then you have a mux here that will either take this signal or 0 based on some combinational logic that compares this value to a given counter like target value. So there's a little bit more there, but the whole point is you can just mentally think of it like this, and in, for example, Verilog, you would actually write it like this as well, or at least very close to this. But it's all based on just these very simple counters and very simple digital output, and that's what makes these very logically simple. And they need to be simple because they need to be small and they need to be cheap. So that's how we do a very basic divider. If we're dividing the clock by 2 to some power, and again, this comparator thing is basically the only thing we need to do to divide it by, some other number, because we just count up to that number and then do something. So in this case, because the Virtual Boy main clock runs at 20 megahertz, 480 of those clock ticks would be our sample rate of 41.6 repeating kilohertz. So that's where those numbers come from. Is that we take the input clock that has a rising edge and a falling edge 20 million times a second, divide that by 480 by doing this basic counter, and then only doing our logic when the counter's current value is 0, or goes to 0, that is. Then, yeah, that's what we get. So I think the most important thing, again, that I just want to show is just that this interface is still all there is. We have this input clock that goes way too fast, but we can divide it down, and then we're going to do some logic that's periodically going to change an output of some port that then goes through a DAC, which is usually also on the same chip, but then this goes to the speaker, and there's usually more to it. Like if this is on the same chip here, there will usually be some analog circuitry here, a couple caps and whatnot, to smoothen out and amplify this signal before it goes to the actual speaker. You wouldn't drive a speaker straight off of the CPU pins. You could, you just wouldn't hear anything. Plus, I think you might have problems with feedback into the chip, so you may not want to do that. But I mean, the designs around this time for digital circuits were pretty, what I would call cowboy designs, because they're just like when you get into the details of how a lot of these designed, I think it's really fun. One of the reasons why I love learning about old hardware and doing emulators is because a lot of it's really weird. Like they would make some decisions that you would never make using modern components, but it was good enough at the time, and it often very clever. So if for some reason they had some speaker that would actually be loud enough if you drove it off the CPU pins, that's totally something you might see in the era, but I don't think that would ever actually be something that would work physically. So we kind of have to circle back to a couple things here, because if we abstract this again, now we've seen how that can work, and how often that does work, but we still have this same interface for our audio unit. We have a clock, and then we have, I'll draw it with a thick bus here. We'll call this out. I've been calling it D7 through D0 for like data 7 through data 0, but it's really the output, and it's like a 7 down to 0, for example. It may not be 7 to 0. This would be 8-bit sound. This might be 15 down to 0, which is this is just one kind of notation for writing this, but I could also just say like this is like 8-bit or something. In the Virtual Boy, for example, it's 16-bit. Super Nintendo 16-bit. I've seen 12-bit. Oh, does it move away? Are you sure you have the right sample rate on that? You should also try dividing it one more time just to see. The 15 kilohertz is pretty high, but you should at least hear I would expect to hear at least something. But what I want to impart is that this is really like the only interface that we have here. So we could model this different ways in code, but I'll just show you how I model it in RushBoy. So remember, our clock goes up and then down. It has what we call rising edges and falling edges. But this right here, we generally call a cycle. One rising edge followed by one falling edge. And then all the way, it includes this time between the falling edge and the next rising edge. So this is the entire period. So oftentimes with emulators, you don't often emulate both edges. There are some systems that do. In fact, C64 is one of the notable ones where the CPU has access to the bus on the rising edges of the clock, and then the video chip, the VIC, has access to the memory bus on the falling edges. And this way they don't compete with each other. There is still some competition because it needs to read a lot of data every start of every character line, and then in which case it actually sends a signal to the CPU that says the bus is not available for a few cycles early, and then starts taking over the bus. But that actually sounds about right, 8littlebits. That at 18 kilohertz, you should, something is happening. Might not be able to hear it. You do want to be careful with turning that up too much. But yeah, so in RushBoy, for example, we don't model both edges of the clock. We only model that a cycle happened. So the VSU, which is the sound chip here, just has a function called cycles, and that takes a number of cycles. And the reason why we do it this way is just so we have less call overhead. So we don't call this every cycle the machine steps. The CPU will step some number of cycles, and then we tell all the other hardware units that many cycles happened. So in this case, we take in the number of cycles, and then I take in something to dump audio. I'll get to why I do that in a minute. But then the only thing that this cycles function does is it just loops through all the cycles and then just does some stuff every cycle. So it's exactly like what I described, where here, there's these different clocks, and they're all just modeled by different counters. In fact, ideally, it should only really model this one every cycle, and then whenever a sample clock happens, then we update all the other counters, because all of the other counters are multiples of that sample clock period, as it turns out. Except the noise clock. That is different. That one's very high. So the interface here in software is that we tell the audio unit that so many clocks have happened, that so many clock cycles have happened. And what it's going to do, we tell it that, and then we also give it, I guess I'll talk about this now. We give it what I call an audio frame sync. Now, if you're familiar with the term sources and sinks, source is where stuff comes from. So for example, if you have an array of integers, you could call that a source if you iterate over the array and pull all the things out. An array could also be a sink if you put a bunch of things in it, and that's basically what this is. The audio frame sync, if we look at this sync interface here, which is in syncsrs, it just has an append function. I may refactor some of these details at some point, but this idea will still stand, that you give the hardware unit a sink to put output stuff into, and then you tell it how much time has passed. So the idea here is that if enough time has passed that a new value would have been put on this bus, then it calls the append function on that sync. So for example, this when the sample clock happens, then we say self.sampleClock, which I just put in another function for convenience, and I give that the sync. And then this will do all of the audio mixing, which is all happening in the digital space. So like the block I showed earlier only generated one pulse. This has several such voices that will divide the clock and then run some counters and take some bits off of those counters and then run them into pulse waves. And then all those get mixed digitally just with some basic adder circuits. And then the output, in this case, it's also stereo, but the only difference there is that we have this output thing is actually 2 buses, and then there's 2 DACs and 2 speakers there. That's the only difference, really. But yeah, all that happens, and then when it generates the new sample, it appends to that sync. So the idea that I'm kind of getting at here, and we got to talk about timing. It's kind of, maybe I'm not explaining this in the right order, but I think it's very important in an emulator generally to make a very clear distinction between real time and emulated time. So when we tell the audio unit that a certain amount of clocks have happened, we're only increasing emulator time, right? Or emulated time. I call it, let's call it host time and emulator time. So in the real world, when we're playing our game, when we're running the emulator is kind of like a black box. And I really don't like certain details to go into the emulator. Like if your emulator knows about system time, like the host system time, that's not my favorite design. Let's just put it that way. What I like to do is have the stuff that's around the emulator, keep the emulator, up to date. So here we want, some kind of system time. And there's going to be some other main loop that looks at what the time is. So it says, okay, how much time has passed since we started running the emulator? So Emi starts here. Or I should say the front end. And you can use just 64-bit integers and count nanoseconds, for example, because if you do that, I think you get like 13,000 years or something before it overflows. So you say this is the time that the emulator started, or that the front end started. So you can just like sample system time here, for example. And then in your main loop, you just loop, however many frames. But let's say you're here. Let's say on this iteration of the main loop, the timer says that you're here. So this is, again, the host time or real time. And we'll talk about where we want to get that from, because there are some details where that's not great. Yeah, you could do this in Flix. That would be fine. As long as you have some way of measuring real time. Then you say, okay, this much time has happened since we started the emulator, or since we started the front end. I should really try to clarify that. So then we look at something else. We look at how much time have we ran through the emulator, right? I like to put it in that kind of way, because let's say we had a frame before this and it said, okay, this is our real time. So let's run the emulator that much time. And it may go a little bit over that, because if we have an emulator that is CPU driven, it may be that the CPU says, okay, actually 5 cycles happened, and so we overshot, this amount by so much. But then we know that we've ran this much time in our emulator. So the next time we sample our time, we're to say, okay, let's actually run the emulator again until we've ran at least this much time. And I really like this way of doing this, because, whenever you check real time, you just see, okay, we'll run the emulator that much time. Check real time again, we'll run the emulator that much time. This should be kind of obvious, I think. And this could be basically any granularity, really. This could be, you want it to be often enough that it's like playable if it's a game console, for example. But it really could be any granularity. You could do this once a year. You could do this once every 13,000 years, but you only get through one iteration or so before things overflow. Oftentimes you'll do this every once a frame. libretro does that. You may do that more often. The Retro Boy front end actually does this every 3 milliseconds, and that's kind of an arbitrary number, to be honest. But I'll talk about why it's so low in a sec. Although it probably could be higher. But that's just kind of the idea, that at some granularity, we're just going to try and keep the emulator up to date with real time. So it's so much easier when your emulator is separated from real time like this, like where the emulator doesn't know about real time. The bootstrapper knows about real time, and it knows how long the emulator has ran. If we look at in Virtual Boy, there's a Virtual Boy struct here, and all it contains is a CPU and some interconnect, and then the interconnect owns all the peripherals and stuff. There's some architectural reasons why we do that in Rust. But the idea is that it really only has two functions. You can make a new one, and I don't actually model reset in this emulator. If you want to reset, you just create a new one. Just reduces some redundant code paths. And then then it has this step function. And the step function, you give it a video frame sync and an audio frame sync. And again, I'll talk more about those details in a sec. And all this does is it steps the CPU. And by stepping the CPU, it says basically run one instruction. It will run that instruction and then tell you how many cycles that came back from it. Actually, there's a little bit more than just the cycles that come out of this. It's how many cycles ran and then whether or not we hit a breakpoint. So there's some debugging stuff here just in the signature, but the whole thing is that it tells us how many cycles happened. So then in the bootstrapping, you'll see that exact main loop that I described, which is in, yeah, see this is in Virtual Boy Core, by the way, which has no bootstrapping. This is just the core emulation, which the advantage of this, by the way, is that there's like no dependencies except in coding, and that's only to read ROM titles. In Virtual Boy CLI, we have Emulator, which is where all the bootstrapping happens. And so here, there's a main loop, which is here, while the window's open and we haven't hit escape. And again, here we sampled the start time, like I mentioned. That code right there is this. And so every frame, we're going to sample the latest time, minus when the time started. So we're going to figure out where on this line we are. We're going to figure out how many cycles that should have happened by now, right? So when I'm running the emulator, going to catch it up to real time, I'm just measuring that time in cycles. That's the only difference here, is that first I get the time from the time source in nanoseconds, and then I just divide that by how many cycles there are, or how many nanoseconds per cycle it is, and we get how many cycles the emulator should have ran by then. And then there's some stuff here that also changes when we're debugging, but the important code path here is this one. While we're running, we're just going to say while we haven't emulated as many cycles as we should have, we're just going to keep stepping the emulator. Super simple, right? So, couple things here. That totally makes sense, right? In terms of driving the emulator. If this were not an emulator, if this were the actual hardware, what I like about this is that this really well mimics what the clock is doing. Because whenever the clock transitions, low to high, that's basically the same thing as telling the hardware to step one cycle. Yeah, Dorotu, I do keep leftover cycles. The way I do that, by the way, you won't see that explicitly. This is a small detail that I'll cover really quick here. I just keep track on my emulator struct. There's emulated cycles, and this keeps track of all the emulated cycles that have happened since the front end started. Again, with unsigned 64-bit integers, we can get to like 13,000 years or something before this is ever a problem with overflows. So we just start that at 0, and then as we're running this, every time we step the debugger, or step the emulator, we add this to emulated cycles, which I think is, yeah, I have a step function down here which actually does it. So here we tell the emulator to step, and then we add how many cycles it went to the emulated cycles. So we do the total, and then we just do that until we get to our target. And so we may overshoot that a little bit, but then that's fine, because then the next time we'll do it, we'll just continue from there until we get to the next one. So yeah, the parallel I really like here is that when you're running when you have real hardware, the clock just happens periodically, and it like sort of sends update signals to the hardware at a very fast rate. But I like that sort of push-based thing is kind of what I'm trying to describe here, is that we tell the emulator that a certain amount of time happened. The emulator doesn't ask us how much time happened, because then we have threading issues or bootstrapping issues, or if we want to do something like build a hardware debugging rig for our Virtual Boy, it gets harder to bootstrap all of the serial port and stuff that was actually super easy here. And again, if we want to stick a libretro front end, then this stuff doesn't change. It's this stuff here that changes, which is the stuff that should change. The emulator core itself is the exact same code. No worry, Mojo Bojo. See you later. Exactly, move away. Yeah, it is really similar to those kind of game loops. Extremely similar to that. Like if you need something that's going to run at exactly 60 FPS, you just keep track of, okay, how many 60 FPS intervals have happened since I last updated? Just keep doing that. Very, very similar to that. I think the fact that cycles are integral values actually makes it easier. Especially since the you know that the system isn't going to have a smaller time step than a cycle or a half cycle in some cases. So it's actually pretty nice. Did I do that math wrong? Is it 584 years? Oh well. Think we'll be okay. Yeah, if you explicitly track the leftover stuff, then it might be a little more annoying, but if you just keep track of the total, then it's pretty easy. But again, the important thing here is that it's push based, and that the emulator itself doesn't care about this stuff. So, as I mentioned earlier, with like the audio hardware or any kind of hardware, because video hardware actually works really similarly to how I described audio here. So I'll actually talk about this for a second here. So we had our audio unit, and it had a clock, and it had some kind of output data bus. Well, it turns out video is exactly the same. And some kind of output data bus. Now, oftentimes, this is, for example, you might have like a 24-bit bus for 8-bit R, G, and B signals. And then you might have like a 24-bit bus where you have, RGB. And then you might have a clock coming out of this too, like a pixel clock. And then this will, send a pixel to some other thing at the rate of this clock. And this stuff's actually kind of common, although you may not have RGB, you might have Luma and Chroma. Really depends on the chip and depends on what you have after that. A lot of the times, this is kind of the interface you have nowadays to drive, for example, an LCD. Like if you buy a little LCD display on Adafruit or something, it'll have a very similar interface to this, where you just clock out RGB signals. A lot of the older ones will have actually analog stuff built into the chip, which is a lot less common now. It's usually only digital stuff that's on those chips. But that happened back in the day. I'll get to Dark Second. I'll get to time sources. I'll get to that. That's what I categorize that part under. And I'll get to that in a sec. But I want to talk about one thing first. So I'm going to remove some of these details. But the point is that you have, some kind of clock or something that has kind of a push-based update. And then maybe there's a new value on this output bus when you do that. Maybe there is. For example, if you just updated the audio for one clock, this value may not have changed. Or the video may not have produced an entire frame. We basically quantize the output of a lot of this in an emulator context to say like, okay, well, in terms of audio, we actually care about the exact samples that came out. And in video, we care about whole video frames that come out. So if we just update this with like one clock, then this value may not have changed. But sometimes it'll change. If we, for example, if we strobe the clock 480 times on our Virtual Boy emulator, a new sample will be produced. So this unit will then push a new sample into that sync. And the way I've modeled the syncs is it just has an append function, so the audio unit doesn't care about where in the sync it is. It's just going to push new values onto the sync. So every time we call this 480 times, or call it once with 480 or a number larger than 480, because if we call this with for example 1,000 samples, this will do 2 of these, and we may have called that on an edge where it was really close to doing another one. So it's just going to append as many as it needs to. Video works the same way. If we tell it that enough clocks happened, that even several video frames are produced, this will produce several video frames and put it in the video frame sync. And again, we're basically just quantizing here, just because that's kind of what makes sense for the output of an emulator. In the real world, it's very common that you'll have sent out half of a frame. It's very common for LCDs and whatnot to update progressively. And so you'll be producing output out of this every pixel, and it's sort of a continuous signal that's clocked, and that will actually happen progressively. There's the Slow-Mo guys just put out a video like a week or two ago where they talk about TVs in slow motion, and you can see that actually happening. But for an emulator, we only really care about sort of whole frames. And a frame of video is obviously a 2D image. A frame of audio, I've been talking about it as if it were, one sample. It's usually 2 if it's stereo or something, and you can sort of visualize that as sort of parallel syncs. But the way I have it modeled is you just have one sync, which just has 2 values for every sample, or for every frame. Yeah, CRT guns are really cool. But the form here is super general. That we have sort of a black box, and we have a push base update, and then maybe this outputs into a sync. And I'm really happy with this architecture because it turns out to work out really well. So as long as we, update and we tell it that enough cycles passed, that, an audio frame is produced, or that audio frames are produced at the right rate and video frames are produced at the right rate. Because remember this, this scales to the entire emulator. Where if we tell it, some time passed, this will output to, the audio sync. This will output to the video sync. Maybe. When it does, we care. But all we care about is that we're updating this often enough that this will produce enough audio frames to go and send to our sound card, and enough video frames to go send to our GPU. So then we get to synchronization, right? Because we need to be able to basically, I had that thing where we were going to measure how much time went by, and then we would, periodically update the emulator. I drew it kind of like this, so I'll stick with this drawing. This is time. This is emu time. So that E got really excited, didn't it? So yes, sir, too. That's exactly what I'm gonna talk about now. I will totally answer that in a sec. Because that is a decision we have to make. But first of all, what I want to talk about is where do we get time from? Right? Because where we get time from determines our ability to, produce the exact amount of samples or the exact amount of frames that the user expects the system to be running at. Hey, Pelicus. So so we have to, before we decide what kind of time sources there are, we have to enumerate kind of what our options are. So one of them might be, oops, keep doing that. I'll actually switch to text for this part because we have system time. This is easy to get a hold of. For example, you could do precise time nanoseconds or something, which I believe is what we use in the RushOboy front end. We could do, this is also often accurate, which we'll actually get to that a little bit. But so there's system time. There's, let's say there's video time or vsync. This also tends to be fairly easy. Somewhat actually, I'll say this is not very accurate, and usually the wrong rate. Or let's make that often. So for example, there are systems like the Vectrex which don't even have a frame rate, you know, so it doesn't really make sense maybe to use video time. Sometimes your monitor refresh is 60 hertz, but your system's supposed to run at 50 hertz or 49 point whatever. I mean, it literally could be anything. The reason why I use nanoseconds and not milliseconds is just because it's easy to get a hold of time sources that will give you nanoseconds. And oftentimes, there are more CPU, like there are multiple CPU cycles in a millisecond, and sometimes they don't divide that well. Is why I do that. Because I want to work at a cycle level, and at least in the case of the Virtual Boy, there's several cycles per millisecond. So I want to be a little tighter than that. Although I don't think I have to be, but yeah, doesn't really matter. But like in this architecture, in RushOboy, for example, as long as we know a number of cycles that we want to run the emulator, then we're fine. So we could get that time from anywhere, and that's why I want to talk about different places where you could get that. So we get it from the system time, get it from the video time. Of these two, I would almost always prioritize system time because it's going to be a lot more accurate. It's going to be just as easy to get a hold of. You may end up with some frame tearing or have to do vsync, so you may end up with, you know, sometimes you'll display a frame for 2 video frames on the host machine. Sometimes you'll display it for less and you'll output more frames than you actually have to. But generally it keeps your code very simple because you just don't really have to think about a lot of that stuff. And yeah, the inaccuracies of video time are just often not what you want. So another one you have is audio time. Audio time can be harder. This is very accurate, by the way. Or actually, I should say this is also accurate. I'll get to what I mean here, but yeah, you can actually render. Yeah, exactly. You can for Vectrex render every frame on the host machine, but yeah, you have to do the CRT phosphor decay. Because then with Vectrex, you kind of just have to pick a sample rate where you want to sort of sample the phosphor, as it were, to produce an image. But yeah, so this can be harder, but it's usually very accurate. But here's the other thing, may not be available. For example, if the user, if you have a front end that can enable and disable sound, you may not actually have this available. So yeah. So what I like to do when considering these options, thanks, Taru. I at least pretendeth to knoweth my shitteth. So one of the things to be aware of here, and I mentioned that system time and audio time are both pretty accurate. So I'm going to put these together because these are usually the ones you want to use. I tend to prefer them in this order, just because again this isn't very accurate. And if you output frames at a different rate than your refresh rate, you're usually okay. so this is going to be the most accurate, but it may not always be available. So then you kind of want system time. The reason, though, that you don't just want to take system time if you have, both of these available is that while both of these are fairly accurate and fairly granular, they may not actually agree with each other. And it may be kind of counterintuitive, but the idea is that your sound card has its own system clock, and your PC also has its own system clock. And it's actually pretty often that what time your system thinks it is and what time your sound card thinks it is slightly different. And that actually does become a problem, because if these don't agree, you're producing either slightly too many or slightly too few audio samples if you're using system time as a time source. And what happens when you do that, so the way audio often works in a modern system, I'll just draw this down here, is you have a little buffer. And usually this is kind of an abstraction. There's more stuff going on here. You have what's called a read pointer and what's called a write pointer. And what you do is this read pointer, the hardware will just sit here and make this loop over this buffer. This is often called a ring buffer, because like asteroids, when this goes off one side, the read buffer will come back onto the other side. And so you can kind of imagine if we bend this into a circle, you get kind of a ring. You can imagine it like that. But the read pointer's here, and it's going to read stuff. And then the write pointer, what we're actually going to do is we have a couple options. We could either set the write pointer in front of the read pointer and always try and write in front of it. It turns out the better way to do that, little more robust way, is to let the read pointer be in front of the write pointer, and just have it so that we check what the read pointer is, and then we fill in this many samples, and then we just do that in a loop. And this way, the read pointer won't get to the data we just written until it loops back around. So then the length of this buffer actually determines latency, which is the time it takes from when we wrote a sample to when we hear the sample, which is going to be a full, buffer rotation before we do that. Yeah, it's an asteroids buffer. But that's it really that's going on here, is that whenever we produce samples, we're going to write this much. So when I am talking about using the audio time as the time source, I'm really talking about using this read pointer as a time source and synchronizing to that. Because here's the thing: if we produce slightly too many samples, what's going to happen is that instead of our read buffer and write buffer sort of oscillating around roughly the same distance between each other, the write buffer will eventually move a little bit faster than the read buffer, and it will overtake the read pointer. And what's going to happen is that then suddenly, instead of writing safely behind the read pointer, we're actually writing in front of it here. And that can, so if the read pointer is playing like a wave that it had, and then suddenly you wrote new data here, which is just like a wave at sort of a different phase, this right here, this transition, it'll look like this is the old wave, and then suddenly you wrote this for your new wave. When the read pointer goes over this, remember your speaker is going to move from up here to suddenly down here, the speaker cone. And so this will be very, very audible as a loud click or pop. So this will happen in the case that if we're producing too many samples, the write buffer will overtake the read buffer. If we're producing too few samples, this same case will happen in the modulo, but what's going to happen is instead of the write buffer overtaking the read buffer will lap the write pointer in the same way like a racing game would happen. The read buffer laps the write pointer, and then this exact same thing happens because we haven't been able to write new data fast enough, and then the read pointer suddenly reads where our discontinuity is. I didn't know that that's what the ScumVM video decoder does, but that's exactly what I think it should do. Because here's the thing, we got it when we talk about which time source to pick, we have to talk about consequences, right? So the consequence for not being in sync with our audio time is that we may get clicks and pops, is basically it, because this stuff happens. What'll happen is right after this happens, like if the write pointer overtakes the read pointer, it kind of gets farther away again until it loops again and then kind of hits it again. Every time they cross each other, for whatever reason, you're going to get a click or a pop. And it sounds very bad. Earlier versions of BeastNest, for example, at least in the accuracy profile, was really bad at this. I mean, I'm talking a while ago, like 2010, 2011, but that's just an example that I can think of. Eightlittlebits says, does the audio buffer always end up with a fixed timestamp or time step, or can the step to emulate differ? I'm not entirely sure what you mean, but let me answer what I think you're after here. So we can always write however many samples we want into the buffer. Generally, we want to write enough that it fills the spot behind the read pointer, and also there is some time. So if we sample the read pointer, and then we write and fill that in, the read pointer will have moved by the time we finish that. So if we only step the emulator so that the emulator will have produced this many samples, we're going to be okay. Because even if we overshoot by like a sample or two, the read pointer will have moved by then, so we're going to be okay. So it usually stays pretty consistent, but it will vary a little bit. But it's fine because we have sort of the whole buffer as sort of safety space for them to move around in. So we try to keep them at the same distance from each other, but that does vary a little bit. And that's just something we have to live with because we are running, two different systems with two different clocks. So this ring buffer is basically our FIFO. But yeah, the read pointer will be at a very fixed rate. And then our write pointer, we try to keep it that fixed rate, which we usually can do pretty well because our CPU is usually running quite a bit faster than it has to. Yeah, I bet, Man Moose. So you're probably very familiar with this particular artifact. So that's why we generally want to choose the choose the audio time as the thing that we want to sync with. I just realized I'm streaming at 60 FPS. Can you guys even tell? That's probably why things are buffering for you guys. I'm really sorry about that. I totally forgot. I can't change that now. I streamed Super Nintendo stuff. That's why that's happening. Sorry about that, guys. I just realized that I was streaming that. I usually do 30 for the emulator streams. Anyway. Yeah, so that is that's a good point actually, Mad Moose, is that while the read pointer's position will increase monotonically, like it will increase at a fixed rate, the size of this buffer is something that we have control over. So if you're really worried about it, you'll make a larger buffer. The consequence is that your latency is larger. So whenever you write a sample, you won't hear it for a while. So like a pretty extreme latency for an emulator might be 200 milliseconds. But I've seen it, options for it to go up to a second just in case. For our 64K stuff, actually, our synth is kind of slow, so we have a 1 second buffer on that, and then we just time the demo 1 second behind, so it all works out. I think right now Rushto Boy uses 100 milliseconds, and that's pretty standard. Yeah, you totally could do that, Drew. I don't know if I'd recommend it. It might be better sounding than clicks and pops. That is something you could do because again, the problem is that you have this discontinuity within the signal. So if you did that kind of slowdown thing, that might actually fix that problem. So you might be okay. Because then at least you're always keeping your right pointer at the right position. So maybe that works. That's not something I think I would try, though, to be honest. But that should work. I don't see any reason why it wouldn't. That's kind of a clever idea. Oh, I didn't realize someone in Nestive did that. That's cool. So yeah, it should work. But that's why we generally want to do that. So just to compare this, what's the consequence for missing video time? Is that we display a frame for 1 frame too long. That's fine. You know what I mean? Compared to the alternative. Clicks and pops are really drawing to a user. Leaving a frame on the screen for, you know, a host frame too long is usually not a problem. So that's kind of our why we prioritize these in this order. But again, remember, audio time may not be available, but then system time will give you something pretty accurate. Also, video time may make sense in some scenarios. For example, if your emulator runs at the same refresh rate as your monitor, and audio is not available, then video time is actually a great time source, because you may be running, you know, slightly too fast or slightly too slow, but it's going to look perfect in terms of your refresh rate. So there is still some validity to that approach as well. But generally, this is what you want to prioritize. But the thing is, this is what I like about this. The only thing that's different about any of these is that these are just different ways of measuring real time, right? Because as long as you have a way to get how much time has passed from these, then you can just tell the emulator to, you know, run that much time. And if everything works correctly in your emulator, which that's a whole other thing, it will produce enough audio samples and it will produce enough video frames that it will be coherent. And so that architecture still stands, where you have, you know, some kind of emulated thing, and then you tell it some, you know, time went by, and it produces its output. And the reason I feed the buffers in every frame is because there's really no real overhead to doing that. And you can also abstract it. In Rust, it really helps to do this, actually, because then you don't have to have the emulator owning the buffers, which is pretty advantageous. There are some details, by the way, with, for example, when it produces video frames. In Rust.Boy currently, we actually have storage for each individual frame, and then we do some passes on that to, like, because the frames are actually double wide stereo frames, and then we do some passes on that'll make it, you know, RGB here. And there's some other things too, and I actually want to re-architect that. I actually want it to, I want to give the emulator knowledge of pixel formats, so that it can actually write into the buffer a little bit faster. But for audio, we really haven't had any issues like that. So that's kind of how I do it. I just run that. So yeah, so now I wanted to talk about what you mentioned earlier, Drew. If you look at emulator RS, so again, this was the same thing where we figure out how many cycles the emulator should have ran, and we just run it until it does that. But then what happens? Well, there may be new data in those buffers. So then we do this. If the video frame sync has a new buffer, and of course you can see up here, I have what's called a most recent sync. So yes, as an answer to your question, if the emulator produced multiple frames, I'm only going to take the last one. This is a decision that, like, you could handle this whatever way. You could even blend frames if you wanted to, or you could buffer frames and then display them over time, depending on how your host system works. Or if you're capturing video, for example, you actually want the intermediate frames. So that's also why I did it this way. And so that we could actually capture those just by using a different implementation of the sync. So it really depends on what you're trying to do. But in the case of the front end for Rust.Boy, which is when you're going to play games, you really only care about the most recent one. And then there's also an audio frame sync here, which I just implement as a vecdeck because it's just very easy. So then after I've run the emulator, I just check those buffers. If there's a new frame, I grab that out, and then regardless of the audio stuff, I just append that to audio buffer sync. This is you can think of this as a separate sync than the one I give to the emulator, but it's really just kind of details. The way that this works isn't terribly important, but I just wanted to show that this is a real architecture that really works, rather than that all these particular details are the important part, which is not the case. The important part is this kind of push-based timing, which I am trying to advocate because it works out really well, and it really closely matches what the hardware is doing. So the rest of it really is all details. Thanks, Drew. I appreciate that. I'm glad you do, because I did think about it for a while. And there are details with, like, how the sync looks from the emulator's perspective, and some other things. But generally, I'm pretty happy with this. But this allows you to do a bunch of stuff. Like so in Rush to Boy, we do that update every basically as often as we can, but then I sleep the emulator for 3 milliseconds between iterations of that main loop. And that's mostly just kind of an arbitrary number. We want to sleep at least a little bit so we don't stall the CPU. If it's too short, we're going to spend like more time than we have to updating the emulator. If it's too long, then we're not going to be able to keep up, and then the emulator will run too slow, and I don't really have any way to correct that in the Rush to Boy front end right now, but I don't really care about that at the moment. Moveaway says, are there downsides like input latency? And I would say it depends. I think that comes more... I don't think there's any downsides to that in terms of this architecture. In terms of which details you choose to implement it, like how often you actually do that update, then there might be. You generally want to check input like once per frame, at least. More than that, you're gonna have to be pretty sensitive to notice. Rush to Boy does it as often as it can, I think. Actually, no, I don't think it does. I think it only does it when it gets a new video frame, then it updates the window. Yeah, so it only does it here. We only update the key state when a new frame is produced. So every frame we do update keys. I think libretro also does it only that often. No, it's not so much that the overhead of the emulator can be a problem for emulation, but it can, like, you can use too much CPU updating your emulator, because the thing is, you do have some overhead whenever you do all that dispatch, whenever you have to step the emulator and update all the buffers and everything. So you want to sleep kind of as much as you can, just generally. I think honestly though, this 3 millisecond thing is pretty arbitrary. I think I might change that to 1, for example, and it would be okay. I wouldn't want to do it too much more than this, just because right now Rush to Boy is kind of slow. And that's another problem. And you definitely don't want to not sleep, because then you're using 100% CPU when you don't necessarily have to, or at least a full core, which is not going to show up as 100% in your task manager. But I think you know what I mean. But no, I can't imagine the emulator updating too often and then that being a problem for the emulator, but it might be a problem for, other parts of your system. So that's at least why you want to sleep some. I think, honestly, I took this 3 millisecond thing because that's what I would do on audio threads for stuff. Like in our synth, for example, there's a loop that runs and just sleeps this much. That's kind of arbitrary. But yeah, the rest is details. For example, Rush to Boy will run that main loop where it updates time and then updates the emulator and then flushes the syncs. It does that every 3 milliseconds, or it ends up being a little bit less than that because, of course, all of this update stuff takes time. So it will do that at most every 3 milliseconds, but it may do that less often. In fact, it probably does that less often on most systems. In fact, on a lot of systems, it does that a lot less often, which is not good yet, but we'll fix that. Yeah, you can totally sleep to try and keep up with VSync, for example. That works totally fine. As long as you're accurately sampling time once you've done that, in order to make sure like you don't miss audio frames or something. But yeah, you can totally sleep a variable amount. That's not really a problem. I just did this because we don't actually do like buffer swap or anything until a new video frame is produced. So doing this just kind of made enough sense. Keeps the main loop pretty simple. But that would totally work if you do that once per frame, for example. As long as you're sampling time correctly, how often you do that isn't terribly important. Moveaway, I think you're talking about the taskbot thing from was it AGDQ last year? I think it was. Well, I mean, if you use the same architecture, but then you just did dynamic sleeping like you're describing, it'll totally work. just as long as you sample time properly when you wake up and start processing things. But that totally works. 8littlebits, yeah, it'll introduce 1 frame of input latency, but that shouldn't be a problem. If you run a whole frame and then sleep, depends on how long it takes for you to run a whole frame on your host CPU. But I can't imagine that's a problem. Again, the 3 milliseconds thing in mine is pretty arbitrary. What was I going to say next, though? Yeah, the rest is still details. So, for example, libretro, when you implement a libretro core, so we can look at the RushToolBoy one, it's kind of a mess right now, but that doesn't really matter. You have to expose a function called retroframe, I think. Might be retrorun. And so that'll run 1 frame. And then if we look at 1 frame, it just expects that we, step the emulator for a whole frame. So I do exactly the same thing here, where I've kept track of how many emulated cycles there are and then the target emulated cycles. So I just take target emulated cycles. I just add, the amount of cycles that 1 frame takes to this every frame, and then do the exact same thing while system emulated cycles is less than target emulated cycles. And then I step that with these syncs. And then the video stuff still works. We do a different video refresh callback that we call. And then the audio stuff, I think I have audio output sync, which should call the appropriate, currently calls the appropriate audio callback from the libretro host every sample that actually happens. It's possible with libretro that you fill your own buffer and then send it the whole buffer, which should actually be a little bit faster. So I want to make that change, but that's just a different implementation of this sync. It'll buffer the audio first and then send it to the host. Yeah, 8littlebits. As long as the emulated system has enough time to process, has enough time to keep up, then you can keep sleeping. That's really your only concern, is that you don't want to miss any audio samples within your buffer latency, and you don't want to fall behind real time. You're always going to be naturally a little bit behind, in the same way that when you're writing to an audio buffer, you're behind the read pointer. It's kind of the same way with this, where as you're sampling time, you are always going to be a little bit behind. But as long as you never progressively fall more behind, then you're fine. So yeah, the rest of this is still details about how these syncs work, I think, which is basically how audio APIs work. And that really depends. I think the libretro stuff, for example, is actually really easy to work with, especially with this design, because as I mentioned a second ago, you can just it'll give you a callback, which has a certain form. Let me see. I think I have this in here. It'll give you an audio sample callback. So whenever your emulator produces a new audio sample, you just pass it into libretro. And then video refresh does exactly the same thing. So whenever the emulator produces a new video frame, you just hand it off to the libretro host. And it totally works. Yeah, exactly, Drew, too. You want the hardware to generate those frames if it can, but you only want to take the latest if you want to, keep up with timing and stuff. But yeah, you could totally route it up differently. So like a different bootstrapping for RushToolBoy might be that it does that, or might even have 2 different kinds of syncs, where it like has one sync that's just a buffer sync that then outputs all of the output to both, a video encoder sync and the display sync. And that would all just work. The emulator core itself doesn't change any code in that case. It's just the bootstrapping for the emulator. It took me a minute to parse what it meant by pulling, but now I see what you mean. 8littlebits. But yeah, that's also what I did initially with RushToolBoy. In fact, I think in Rush2Boy CLI, we have a wave buffer, or wave file buffer sync, which just dumps all this to wave. And I did that when I was adjusting the timer, I think, actually, is when I did that. But yeah, that totally works too. As long as you have, hopefully, the same sample rate that your thing is going to produce. That your emulator's audio unit is going to produce. In terms of actually interacting with the audio APIs, yeah, so libretro is really easy because the first thing that the libretro core does, even before it calls your init methods, is it starts, where to go? Here. It gives you a bunch of callbacks. So it just calls a bunch of functions that say like set video refresh, set audio sample, and it gives you function callbacks that you store on some structure. And then you just call those whenever your system has produced those new things. I think though with the video refresh, you're only supposed to call that when in run frame, but audio sample, you can call that basically anytime. Although I only call that also from run because that makes sense. So that's really easy. When you're working with more low-level, system-level audio APIs, they're actually really complex. And it's because the simple model of, the read, write pointer and ring buffer, you can often recreate that abstraction over any system audio API, and that's not really a problem. However, a lot of them are lower level or have many, many more configuration options that you could use that it may not be that easy to set that kind of thing up. And you may have to run multiple threads and, for example, do the read pointer thing yourself. So there's some annoying details with that, but it's kind of specific to those APIs. And those APIs should be that complex because for audio at a system level, there are many, many use cases more than what I've described today that you want fast paths to take advantage of, and you want things like hardware accelerated playback or to be able to play like hardware decode MP3 or something. So you want a really full featured system level audio API, even though the audio API that your emulator bootstrapping cares about may actually be a lot simpler. So in Rush2Boy, there's a CPAL driver thing, which is just my own module. And so here we have a ring buffer. I've implemented an iterator for that because this also does some resampling, and this is another thing that I haven't talked about, is that if your underlying audio API, like let's say in the Virtual Boys case, the audio unit will produce samples at a rate of 41.6 repeating hertz. Now the system level audio API may not allow me to have an output buffer that has that sample rate. And in fact, on Windows, for example, it doesn't. So what you have to do is you have to resample the buffer. And audio resampling is a whole other thing that isn't too hard if you kind of know how to do it. I'm not going to talk too much about that here, but I do what's called a linear resampler, which is just going to pull buffers from the ring buffer that I described earlier, or pull samples from that, and then sort of linearly interpolate whenever it has to do, like fractionally between two samples. It's actually pretty simple, but you kind of have to think about how to do it. And linear is not great. There are way better ones, but this one's very simple, very fast. But basically what it does is it has a ring buffer on the actual hardware. That's the hardware sample rate. And that ring buffer is pulling out of the ring buffer that I described earlier, but it's pulling it out and resampling at the same time. So we get slightly different read pointer rates. But we only watch the one that's not the one that goes to the hardware, but the one that's being resampled. We watch that and then have our write pointer behind that. And so there's a fair amount of details there and some threading stuff that's not very pretty, but it's all here. So if you do want to look at it, that's cpaldriver.rs in Rush2Boy CLI. So it is there if you want to look at it. It's not very pretty. It's not very nice. I mean, it's not too bad, 230 lines of code. And that's built on top of CPAL. Which is cross-platform audio library in Rust. And that uses WAS API on Windows, which is why you can't just request any sample rate because it won't do any internal resampling. So you have to do it yourself. Direct Sound, for example, can do that. I know that there are audio APIs on Linux that can do that as well. Don't know that much about Core Audio. I don't remember that. I think it can actually internally resample, though. Man, there too. If someone could pay me to do that, I would jump on that in a heartbeat. Yeah, writing AVI files. There's a lot more container stuff there. Although I think uncompressed AVI may not be that bad, but I don't know. I'm not sure. Boo, Danny Fritz. Yes, sync is something like a sync filter is really good. The thing is, you have a couple different problem cases because you have upsampling and downsampling, and both have different kinds of problems. So sometimes holding can be better when you're upsampling. Holding is really bad when you're downsampling. Then again, linear isn't that great either, but I don't know. Lots of trade-offs to those, and I chose to kind of not care and just do a simple linear one. In for example, libretro, the idea is that the front end cares about all that stuff, and you're not supposed to. So if you don't want to care about that, or you don't want to look into it, if you just want to get it to work first, doing your emulator as a libretro core is actually not that bad. If you don't mind a little, if you're in Rust, if you don't mind a little CFFI, if you're in C, then it's pretty natural. So I would actually recommend that at this point. But if you do want to dig into it, then the lower level APIs will work for you. Just another point of reference, our 64K synth, for example, uses direct sound. Direct sound is a really old API, but it does internal resampling, so that makes things a little bit easier, and it's not a lot of code to set up. But it also has to set up another thread that does, the read and write pointers. So like the ring buffer reading has to happen on another thread, and then the ring buffer writing happens on the main audio thread. So I think it actually spawns. No, actually, that's not true. It only has one ring buffer, which is internal to DirectX, and then we fill that from the audio thread, which runs the entire synth, and that's separate from the video thread. But that's neither here nor there. But there is some of those details. It's very common to have like a specific audio thread for producing audio samples, and a specific like another UI thread or something else that's your main thread. In the case of this emulator. Whenever I tell the CPAL driver to have more samples, so here's the CPAL driver buffer sync, which has a mutex around the ring buffer. And when you tell it to append stuff to the buffer, then it locks that mutex and just pushes onto that buffer. And this works perfectly fine. And then the ring buffer on the audio thread will sit there and lock the mutex and read it every so often. And that's just fine. The contention on that mutex is never very bad. Because we only hold the lock when reading if we're actually pulling out samples. So we're actually writing into that ring buffer, the resample buffer. And we're only locking the mutex when we're writing after we've run the emulator. So we already have prepared a buffer of samples, and then we lock the mutex and send it. So it's pretty quick. So. 2 hours. That's actually less than I expected to talk about this, but I really wanted to talk about this because I think this architecture works pretty well, and I think it's relatively understandable. And I kind of also liked that that I get to talk about it in the context of audio hardware, because one of the things I find really fascinating about this kind of era of audio hardware is that a lot of it's actually really basic counters. So the hardware itself is like remarkably simple for what it does if you study it a bit, because there is a lot I didn't go over, like how does an oscillator work, but it is usually, like I mentioned earlier, like some kind of counter that resets at a certain interval, and by changing, like, so I mentioned that we had a counter with like the register, and then let's draw it like this, we added 1 to it every cycle. Well, this 1 can be changed. This 1 can be 16, 8, 4, 2, and then this register can be 10-bit, for example. Let's say it's 20-bit. Then when this wraps around, that's going to wrap around at a certain rate, and that can produce, for example, a square wave, or a sawtooth, if you just take the value of the output of this and send it to your DAC. So there's different ways you can kind of generate those very simple signals. Very, very digital signals. Like these aren't great signals in terms of like aliasing and whatnot, but they're era appropriate, and they're very simple to generate. And that's one of the things I really like about it, and that I think that hit me most when doing the sound chip in the Virtual Boy, because it's all that stuff. Very, very basic. very, very basic counters and just events that happen whenever those counters wrap. And then like audio mixing, for example, is just a very simple, like if you have a 4-bit output from one of your oscillators, and then you want to mix it with an 4-bit volume, for example, that multiplier is actually very easy to make with a couple barrel adders. And so then those can be added together and just take the top bits. If you don't care about things like overflow and stuff, then it ends up being pretty simple. And it's relatively easy to emulate too, as long as you have the right idea about it, I think. I think it took me a while to fully understand it, to be honest. But now I think I have a pretty clear mental model, and I think with what I've described today, I think that should be relatively easy to understand. Or, easy for some, hard for others. Everyone's different. Love your neighbor. But yeah, shouldn't be too complicated. Are there any questions or specifics that you guys would like me to clear up? Because I'm basically, that's my spiel. I'm basically done. And I'm gonna go watch an awesome anime called Food Wars after this. So if you guys have any questions, go for it now. By the way, thanks again to 8littlebits for asking about this, because I think this was something I wanted to talk about for a while, and this is a good opportunity to do that while working on the libretro stuff. So I'm pretty happy about that. Thanks, Sindels. Sindels. Thanks, Drew. Appreciate it. I think this will be one of the more consumable streams, at least. Emulators and chill, exactly. That's basically my apartment. And that's part of the only reason why I'm the only one in it. Or part of the reason why I'm the only one in it. Thanks, Future Sector. Now, Emulators in Chile was when I was at my mom's place. Thanks, Grumblex. Appreciate it. It's pretty great. Dynamic memory allocation. I think if nothing else, I hope that a lot of these explanations kind of demystified a lot of it, because I mentioned there are a lot of details here, but at the same time, we actually covered so much stuff in terms of how this really works. So, and it's all related, like timing and audio in general. I mean, it's just, if you're doing audio, you run into timing right away. So, Danny Fritz, have you thought about contributing to other emulators such as Dolphin or RPCS3? Not really. I mean, I think those projects are awesome. Like, they're really cool. But they're really big projects, and it seems to be that whenever I take a look at one, there isn't very much low-hanging fruit. A lot of contributing to emulators like that requires kind of a lot of buy-in mentally, if that makes sense, because you have to learn not only about the system that you're trying to emulate, you often have to do a lot of reverse engineering about that for emulators at that level, which I'm totally into. I think that stuff's awesome, but you also have to invest a lot into the architecture of other emulators. And for me, in my free time, I tend to prefer building things from scratch, because it is a little bit easier. Like, you do more work because you have to do everything, but at the same time, a lot of that work feels a lot more natural because you're not trying to learn both the system and someone else's architecture, if that makes sense. Now, in some cases, that's not the case, and sometimes it can be really easy to contribute to one of those, but I don't know. I tend to bounce around a lot between projects, and so sitting down and getting really familiar with someone else's architecture for a project like that seems to be not the most appealing thing for me. Yeah, that's exactly it, Danny. There's a lot of yeah, a lot of overhead to getting started into something like that. I could also see how C++ is a bit scary. I don't know if I feel the same way, because it especially a lot of those ones actually tend to use relatively basic C++. It seems like kind of C with classes kind of C++, which is not that bad. And with emulators, you can generally separate the units pretty well if the authors have done it that way. A lot of older emulators, the code tends to be quite bad, to be honest, and like difficult to read. But in a lot of the newer code I've seen, it tends to be relatively straightforward, except the systems themselves are bigger. And so then you're dealing more with those issues, but that's kind of a different thing. I have been watching the development of Yuzu a little bit, but only briefly and only through Discord. But I mean, it's being done how I would have expected to do it. Like, admittedly, when I knew the Switch was going to be X2 hardware, I did totally get a datasheet for that and started looking into the hardware details, and very quickly decided that if I ever wanted to go down that route, that I would do high-level emulation of the system, and then not really low-level emulate any of that, except unless you had to do like a particular protocol or something, which you shouldn't have to do. I'm also a little more interested in emulating these older systems, mostly because the hardware is a bit simpler, but also more low level. So it's more unknowns in my mind. Like I'm a graphics programmer by trade, so a lot of modern systems are almost too close to what I do, if that makes sense. That I don't feel like I feel like I'm learning a lot about a particular system, in a way that just doesn't excite me in the same way. I don't know. It's hard to explain. But I think Daru has a point here, that contributing to those emulators is a great way to get started if you're looking to learn both about emulation, and also contributing to open source projects in general is a really cool practice. So don't please don't think that I'm saying that that's a bad idea or whatever, that I'm against contributing to open source, because I try to contribute to open source whenever I have a good opportunity. It's just that when it comes to emulators, I tend to like to make my own. I like to feel like I have a whole understanding of a system, and think that's fun. But yeah, I would also recommend at least taking a look with some of that stuff. It's also been rare that I haven't really been a part of those projects early enough to do some of the fundamental work, which is a curse and a blessing, because there's some like I think doing for example, TEV code to GLSL translation in a GameCube or Wii emulator could be really fun, but unless I pull down Dolphin or something and make my own graphics backend, that's not going to happen. So sometimes there's some opportunity there. Like when the Switch came out this last year, I totally jumped on an opportunity to be in the Reswitched group, and I only really did work for that for a couple weeks, and I honestly didn't do that much. Really, I only found one job gadget that got us the stack pointer that got us to ROP, so it was like a very small thing, but it was so much fun to follow that and learn a lot about that process, because like I feel like I generally have a decent understanding of how systems work, and I have a pretty good I have decent experience with GPU programming, decent experience with low level things in CPUs and operating systems, but there are a lot of specifics about reverse engineering that I don't know that much about, and there's a lot of specifics about certain kinds of systems, like ARM architecture 64-bit is not something that I'm very familiar with. So there's a lot of learning that happened there. And there was also a lot that people brought to the table. Like I'm not that familiar with the 3DS. But then a lot of the guys that were made a lot of progress very quickly on the Switch, because the operating system was so similar. So they had seen those kind of object files before, and they knew what to look for in memory. A lot of those things that sometimes you just kind of have to overlap. Like you have to have the right skill, and there has to be availability for that skill to be applied in a lot of these projects. But I think almost any of these projects has a lot of things where if you were looking to contribute, just anyone, if anyone were looking to contribute, there's like easy ways to sort of get your feet wet with stuff. And over time, if you're interested, then that could be a great, team to join if you want to build those skills doing that stuff. So I think it's awesome to look into. I just tend not to do that myself so much. Exactly, Danny. I hate OSS. That was my point with all that for sure. Yeah, the monthly reports from Dolphin are fantastic. They have a really cool cool team as a whole that's very productive, and the write-ups are really nice. Yeah, Chief Detector, I totally know what you mean. In fact, one of the reasons why, so one of the open source projects I contributed to, where again I had the skills and experience, and there was a project that needed those skills and experience, and it was the Core Audio RS crate. That pretty early on, it was going in a direction where it was a bit too high level, I would argue, and I did argue that to the maintainer of the project, Mitch, who is a really, really friendly guy. He runs a lot of stuff with like Rust Audio and stuff. And just through some emails, I just kind of described how I thought it should work, and he kind of agreed. And I went and just sort of revamped that whole thing. And that was one of the things that sort of led to that being able to mesh well with CPAL. So there is actually some of my code down, lower in that part of the stack, which is pretty cool. And a lot of that was totally me also saying like, okay, so I've done audio on Windows with direct sound. What does it look like on OS X? And so that was Core Audio, and that was sort of me learning about Core Audio at the time. And there's still so much more that could happen on that crate, for example. But we just changed the fundamental design so it better matched the system APIs, which made it a little easier to interop with, given the existing docs for that from Apple. Yeah, I think it was Danny. I think because he actually runs a lot of projects, and I think it's really cool because you can dip your feet in a lot of stuff, and especially with Rust, people tend to be really friendly. So like if you put up a half finished crate and just say that like contributions are welcome, because I know that like when I saw that, for example, from my perspective, it was like, I'm learning about this audio API. This doesn't look like the right abstraction, but I'm interested in learning what he was thinking, and just coming in with that, he had an open-mindedness that other people might have ideas to contribute, and I had an open-mindedness to hear his side of things as well. And then it just kind of was like, once we discussed it, there was a certain design that kind of emerged from that, and then we were just able to do it. And there is I think generally a lot of opportunity in the Rust community to jump onto a lot of such projects, just because I'm not a huge fan of rewrite everything in Rust, but there are a lot of projects that are doing that. So you can it's kind of a good opportunity to get in there now and work on kind of the projects that you may want to work on. Stuff like CPAL, I know definitely needs some work. Luton is not Luton. It uses Luton. I can't remember what it's called. Maybe it is Luton, but it's the, like Rust Audio in particular has a project that's just meant to, read and write samples from a ton of different media formats, and like that's a really good place that needs contributors. I saw recently it was I think Lollerpop it's called, LALRPOP. That's one by Nico Matsakis, I think is his name, where he's looking for maintainers, for example. So there's some opportunity there. I think there's those kind of opportunities all over the Rust community, especially, but also generally with emulators. And I know that from talking to the libretro guys, they're obviously very good, but also their project is enormous. So like, especially like fixing bugs in RetroArch or doing those kind of things, there's some opportunity there too. That's actually something I will try to help out with in the near future, because there is a bug in RetroArch. Let me see if I can hit it. I was hitting it earlier today. I just didn't want to show the screen. Okay, so there it is, first try. So in libretro, you're supposed to be able to your core is supposed to be able to, what am I trying to say? The core is supposed to be able to request a certain pixel format. And once that happens, the host, if, like, it should give you an error if it doesn't actually provide that. But oftentimes on Windows, it seems that that call back to the host gets lost. And we don't know why that happens. I think it might be a threading issue, and I want to look into that. But we'll see. Because the problem is you can't query what the pixel format is after that. It's a known default at startup. And so if your call just gets lost, then you don't actually know that you have the wrong format. And so you can't really recover from that, which is why currently it just shows the wrong thing. But a lot of the time it works. So there's something weird going on there. Yeah, I'm pretty new to the libretro community, so I haven't experienced that yet, 8littlebits, but it may just be that I'm new to that community. And yes, there are a lot of those kind of people in open source as well, just because there's a lot of those people in communities, a lot of those people in working environments as well. For whatever reason. Like there are people in the Virtual Boy community too that rub me a little bit the wrong way. But doing fun stuff. I don't know if gluten needs so much work. I know that CPAL could use some touch-ups. Rodeo probably as well might need some additional design. But yeah. Yeah, it's absolutely true, Danny. Different levels of pride and control. Absolutely. With Rustio Boy, it's definitely a mix of both for me because I am really proud of this project and that it is one of the better Virtual Boy emulators out there. But I also try to at least make it inclusive. But I don't get that many like pull requests and stuff. There have been a couple guys like Jay Westfall who did a lot of the CPU and cache stuff, and I think it was because like he wanted to learn that and saw that we hadn't done that yet. I was really happy to accept a lot of that. But with Virtual Boy, it's not the most popular system, so it's naturally less likely that stuff like that happens. But yeah. I think one of the reasons why, like, if people rub me the wrong way, it's usually because we disagree on some fundamental things. And there are ways to not say things nicely. Like, I don't want to name names here, but there is a particular person that sometimes hangs out in the Rustio Boy Discord who, like, if I say that I found something or whatever, this person just says, like, starts quizzing me on things that I may not have found in a way that I think is pretty rude, in a way that I don't think is very respectful to me or the project. That kind of thing I don't like. Or when people say something like, oh, I know this, you don't, so you have to talk to me about that or something. It's like, dude, share your knowledge and be helpful. Don't, you know what I mean? I don't know. Some stuff like that, but it's, for the most part, it's not like that at all. Yeah, the penguin. And that is true. If you are going for a specific vision, you do lose some control when you accept maintainers and contributors. I mean, even in a project like Rustio Boy, like I didn't write the cache code, someone else did that. And one way I could look at that is that I missed out on an opportunity to do that myself and learn about it. On the other hand, from reading his code and then reading like a computer architecture book, I was able to get a good understanding. So it's kind of a stepping stone in a different way. And someone else got to have that experience, which was pretty cool. Although I actually think one of the things that we do in Rustio Boy is I think that the cache, we don't actually use it as a cache. Like we maintain all the entries and stuff, and I think we implemented dumping and restoring. I don't remember. The cache isn't very big because it's actually pretty simple. Clear entries, read half word. Yeah, that's read from the cache. Because I think we always read half word from the system. But we should actually use the cache as a cache. I actually think that might make the emulator a little bit faster. Because if the cache fits in the host machine's cache, then it can actually make a lot of sense. and then we do less branching and stuff based on the interconnect. So I actually think that this could be a little better, but stuff to do on a later date. Sometimes I think about writing such a manual. I think what would be more likely, because there's actually a lot known about the Virtual Boy. The stuff that I've discovered has not been very fundamental, actually. It's just been details like counters for things and some implementation for things. I wouldn't write a whole technical manual because the official docs are actually fairly good, and then there's the tech scroll which another guy is maintaining in the Virtual Boy community, and he likes to kind of keep the guy who maintains the tech scroll. Like, the tech scroll is really good. Let me first point that out. There are some details that are wrong, but at least the later versions are pretty good. The problem is he doesn't develop those in the open, which is one of the things I don't agree with, because it makes it harder to contribute. But when he does roll out new versions, they are good. He does a good job at reverse engineering. So there's a lot of information covered there already. And I don't want to sit there and go through him to get those changes made. I'm kind of a hit and run kind of guy a lot of the time, where it's like, if it's on GitHub, it's really easy because I can just make a pull request and then move on to the next thing. And I would love for that document to be that way, but it's not. There is a wiki at Planet VB, and I've thought about filling that out because then I can do that in kind of a hit and run style. But at the same time, I don't want to write an entire technical manual, because I don't think that's necessary. A lot of that's covered in the tech scroll in the CPU doc, like the official one, and also it's not that hard to find the official Virtual Boy document. And if you can get a hold of that has, really good information. Not all of it's written that particularly clearly, but it's all correct to my knowledge. So, yeah, I just don't think I would sit down and put in the time to write a whole new doc. I think having done the emulator and trying to make the emulator code as clear as possible is a form of contribution there. That is made, probably not as good for random access, but at the same time is, the best of my ability to produce something that is accurate and correct and still relatively readable. But yeah, there is a fundamental difference between the way that I think. So for example, the guy that maintains the tech scroll also is developing an emulator for Virtual Boy, and that is a project that I have decided that I initially wanted to contribute, but I have decided not to over time, because I don't agree with developing a lot of things in secret and then releasing it. I would rather do that in the open to encourage more people to contribute. That particular maintainer is someone that you have to. He doesn't seem to trust other people. He doesn't seem to trust other projects. He may or may not be the same person I mentioned earlier that comes and quizzes me on stuff, and I don't, that really rubs me the wrong way. And I'd rather spend my time, working on something that I benefit a lot from without dealing with that friction. So sometimes in open source, those are sources of drama too, where it's like, okay, I just won't contribute to that project because, I don't have the most fun when I'm dealing with this person. I don't have the most fun when I can't contribute as easily as I would like to. So I'll just go work on something else. Kalt balkong. I think you could learn it if you tried. It might be too confusing now, but if you dug into it, it might not be that bad. Oh, that sounds like a cool project, though. But yeah, the other emulator that I mentioned, it's one of those things that you there's no source for or builds for, and the guy rewrites the core all the time, and it's a relatively unstable project, but the guy does really good job at being thorough, especially with reverse engineering. So it might happen, you know, in a year or two when his emulator finally comes out that it's better than Rustro Boy. But at the same time, you know, like if that overtakes Rustro Boy in some sort of way, you know, I've still contributed something, and I've learned a lot from doing that. So I'm still going to be satisfied with that. I like the term bottleneck, but you can always make a bottleneck bigger or bottleneck wider, at least if it's a knowledge bottleneck. That is so true, Danny Fritz. Anyway, really fun to shoot the shit with you guys, but I think I'm going to go. Because it's been 2.5 hours now. Anyway, this was a really fun stream. Glad you guys liked it as well. Hope to do more like this where it's maybe a little more tangible than just watching me debug shit. But yeah, I want to do both kinds of streams, so keep doing both. Anyway, yeah, probably more Earthbound this weekend instead of demo scene or whatever, just because I'm really enjoying that lately. I would like to continue playing that game to relax. In terms of what's next for Rustro Boy, I still want to work on the libretro front end. Like, it looks fairly stable, but like there was that bug we found in RetroArch. Oops, where'd it go? I did write this whole ticket this last weekend of just stuff to do on libretro, so I'm still going to work on that. There is still the timer bugs that I want to look into. That samples play at the wrong rate. I'm sitting here stewing on how I'm going to debug that, and I'm starting to come up with how I want to do it, where I basically want to rewrite the sample playback routines with the original data, so that I can get it to play back at the correct rate on hardware and at the wrong rate in my emulator, and then start debugging, you know, with that kind of sort of with my own implementation of their algorithm, but in, you know, a much simpler context rather than continuing to reverse engineer those things further. Because I have a feeling now that it's going to be a bug in the timer, and I'm not really sure how that's going to happen or how that's going to work. I may also make kind of a REPL interface for just like doing timing tests for like counting clock ticks and stuff, that I can just run against the hardware, in order to just try and make some notes about some of that stuff. So it'll be pretty interesting, but I kind of got to think about more strategies on how I'm going to do that. Because I do think that there's more to the timer implementation than we're seeing. And at least re-implementing the sample playback routines from various games that I know play back at the wrong rate against, you know, if it's just that in a ROM, it's going to be a lot easier to look at and play with, especially if it's our own code. So I think that will help us at least isolate if that is, in fact, the issue, which is the timer. And I think it is. But I at this point, I don't, like, I'm kind of suspecting that the timer has an internal clock. So I think it might divide the master clock first to something that's like half the clock period of the minimum speed that it goes at, and then whenever you like latch new values and stuff, those only are accepted at the next clock edge of that next divided clock. I'm suspecting there's something like that going on in there, because the timings that I got from reverse engineering those playback routines a while back kind of pointed to there being some kind of time quantization, but not that was smaller than the rate that is the minimum timer frequency, or the smaller timer frequency. So there's some weird stuff, and I would like to dig into that at some point, because then I think that would fix the sample playback stuff. There's still the other bugs with the other, like there's a couple, like there's the lasers in Space Invaders, and a couple other things like golf transitions to demo mode too fast. That might be timer related. It might not be. So there's a lot of stuff for Virtual Boy still, but I'm excited to work on all that. There's also more CPU testing that I want to do, but in terms of the immediate future, the libretro front end is something that I'd like to focus on for a little bit longer. kind of get that more up to speed and then focus on accuracy again. I think that'll be fun. So next week we'll probably just be hammering out some of this libretro stuff. Regular coding week. But yeah, anyway, thanks guys for hanging out. I'm going to go, and I will see you next time.